Hello friends, in the last lecture we have discussed the basics of slings. Now we will move further and understand more about the slings. So let's start the base hitch, the type of hitch. Basically, whenever we are using sling for the rigging, then different types of arrangement are being used. So basically, what exactly is a hitch? Sling configuration whereby the sling is fastened to an object or load either directly to it or around it. What we can do, we can either directly fix the sling, we can either directly fix the sling to the load, okay, their lifting points are over there, or suppose this is some circular shaft over there, so it may be wrap around it, okay. So these are basically the funda over there. So the sling configuration whereby the sling is fastened to an object or load either directly to it or around it is basically called as hitch. Now there are basically four types of the hitch that we commonly use for the rigging application. The first is the vertical hitch, the second is the basket hitch, vertical hitch, basket hitch, chokers hitch, and bridle hitch. We will discuss in every hitch details and how the SWL affected and how the reduction factor is being calculated. The first thing is vertical hitch. The example in front of you is basically of the vertical hitch. Here we are lifting some hook with the help of the hydra, okay. Now here the direct, if we are lifting something directly with a single rope, then it is basically called as vertical hitch. In the vertical hitch, as the hook is free, the hook by which we are lifting up, it is free, so it is free to rotate about its axis, okay. So whenever we are lifting such a case, first thing, the tension will be equal to the weight that we are directly lifting up, and it is free to rotate about its axis. So if the object, if the object is complicated or have some complex geometry, okay, or even it can rotate and hit, if it has some part that can hit something, so what we have to do in order to control the rotation motion, we have to provide the tag lines, okay, tag line in opposite manner, so we can control the rotation. One tag line is this side and the other tag line is this side, so we can control. If it is load rotating clockwise, we can just adjust, okay. The helper will be the riggers will be used for this tag line holding up, okay. The tag lines have to be provided. So first case is of the vertical hitch. You understand about the vertical hitch. Now we will move to bridle hitch and will later understand about other hitches. The second is bridle hitch, okay. Let's move into the bridle hitch. The bridle hitch is like this. Here we are using the here it is basically two leg bridle hitch where two slings are being used, okay. If sometimes the CG is it is basically object having the same geometry, basically the uniform geometry, but sometimes the geometry is not uniform, then we either have to adjust the length using the turnbuckles, or either you adjust using the turnbuckle, or you can have the different length slings also. So it is basically the case of the two leg bridle hitch. It is basically the case of the three leg bridle hitch, and it is basically the case of the four leg bridle hitch, okay. Now how these bridle hitch affect the as working load limit of the sling, we will understand that, okay. Now let us, this is the basic example over there. This is basically the black, it is basically the sling, okay, and we are lifting up a load. This is the yellow, it is basically load. This load has CG over there. So whenever we are making arrangement for the bridle hitch, always remember the CG must pass through the lifting point, okay. The lifting point, the hook lifting point and the CG must be in a single line, otherwise there will be an unbalanced movement will be created, and it will basically unbalanced movement will be there, and it will the lifting will not be proper, okay. It will either rotate this side or that side, it will affect the rotation, okay. The load also gradually changes, okay. So here the lifting point, we are lifting up from this point, and this lifting point is within the CG line, okay. It is falling, the lifting point and the CG line are at the same coincide, CG line and the lifting point are coinciding, okay. This is the basic requirement. Whatever the lifting you are doing, this is the basic funda over there. The lifting hook, the line passing through the lifting hook must be passed through the CG point. So this is the load we are lifting up, this is the sling, and suppose this is having the total weight 2W, and the load on the each sling is coming, this is the W, it is basically the load is divided equally over there, and it is basically symmetric object over there. The tension will be the this sling in the tension. So it is basically a simple arrangement over there. This is the tension and this is angle theta, it is clear, and this is the load W that is equally distributed on the both side. If we resolve this T Okay, about the center we resolve this t, then it will be there are two components of this t. This t have two components, one is t cos theta and the other one is t sin theta, and this t sin theta will be equal to w. The sling, the tension in the sling will be equal to the load that is experienced at this point O. Okay, so t sin theta is equal to w. What t represent? T represent the load on the sling or the tension in the sling. So from here it basically comes out t is equal to w by sin theta. Okay, this theta is called as including angle. What is including angle? The sling that makes an angle with the object is called as including angle. Theta is the sling, the angle made by the sling with the object is called as included angle. Okay, so the tension is given by t is equal to w by sin theta. We already discussed in the last lecture also. It is a basic simple geometry work, that is not that complex. Okay, now how this angle varies and how this angle affects the tension. This is the theta is equal to 90 degree. It is the vertical lift over there. Simple, we have discussed. Here we are using the basically two bridle hitch. Okay, we are using the two bridle hitch. This one is two bridle hitch. This one is 1, 2 and 3 bridle hitch, and this one is 1, 2, 3 and 4 bridle hitch. Okay, so whenever we are using two bridle hitch, 3 bridle hitch, 4 bridle hitch, we have to check the angle that the sling is making with the object theta. Here this is angle theta, the vertical line, and the angle that is making up, that is basically theta. This is angle theta. Here this is angle theta. Okay, suppose this t, we already find that t is equal to w by sin theta, and w by sin theta is equal to basically t is equal to w by sin theta. If theta is 90 degree, the case when we are lifting we are using a single sling, the angle is 90 degree. If angle is 90 degree, then sin theta sin 90 will be equal to 1. So tension is equal to the weight of the load. It is a simple case that we have discussed so far. Here we are lifting hydra, the tension is equal to w. Okay, the reduction factor will not have any the angle will not have any effect over it. When theta is equal to 45 degree, when we were talking about theta is equal to 45 degree, then tension is equal to w over sin 45 degree, 1.414 w. Here it is tension is equal to 1.414 w. Okay, the weight whatever coming supposed to become on the slit, there is a increment of 41.4% weight, more weight. Okay, the sling will experience 41.4% more weight. अगर उसको सीधा उठाते, when we are lifting vertical, then it is w, but when we are lifting at an angle 45 degree, then it is experiencing 41.4% more weight. Similarly, when theta is equal to 30 degree, then this will be 2w. This means that the sling is experiencing 2 times weight. So it is clear that whenever this theta is varying, the tension in the sling also varies up. Okay, if SWL is the capacity 8 into d square, the formula for the sling that we are using it, there must be, we have to multiply it with sin theta. You have to multiply it with sin theta, then we will get the exact WLL. Whenever in bridle hitch you have to find the calculation, then you have to find WLL is equal to SWL into sin theta. Okay, SWL is the safe working load limit of the sling, that is calculated in the formula 8 into d square, and sin theta is the reduction factor. Okay, by this you can identify the what is the WLL of the rope. Okay, that is you have to use. Simple case, this is a simple case. Suppose this self weight of the concrete block is 24 metric ton, you have to lift it up. We are using bridle hitch, 4 slings are there, and all these the common lifting point, the lifting point is passing to the CG. So it is a symmetric object over there. If it is 24 metric ton, then on each sling the load will be coming out, as there are 4 sling, 24 by 4, that is 6 metric ton will be the load. Suppose we are using a 1 inch diameter sling. Okay, diameter is 1 inch. Then SWL is equal to 8 into d square, 8 into 1 into 1, 8 metric ton. Now, in that case, if we have to identify whether this 1 inch diameter sling is sufficient or not, okay, we have to depend on the theta also. So, WLL, the sling, WLL is given by SWL into sin theta. SWL comes out to be 8 into sin theta. If the sling angle, this angle is 60 degree, we are taking the case 1. If this angle is 60 degree, then 8 into sin 60 is 6.93 metric ton. The coming on each individual sling is 6 metric ton. Then 1 inch sling is sufficient for 60 angle only. But if we are taking the angle 45 degree, if the angle between the sling and the object is this angle is 45 degree, okay, then it is 5.66 metric ton, okay, then it will be fail. The same sling, by changing the angle we are able to identify that the same 1-inch dia wire rope sling is suitable when the theta is 60 degree, but it is not suitable for lifting when theta is 45 degree. So the theta plays a very important role, okay. If we plot a graph between the load and the angle, then it is generally found that is 90 degree. It is given that if suppose this is 1000 pound at 45 degree, if we are lifting up 1000 pound, then the reduction, if 60 degree, then 577 pounds load is acting. If it is 1000 pounds, then 707, 45 degree the load is increasing. 30 degree the load is almost same, matlab on the sling it is double, okay, the load on the sling is double. So in this manner there is a zone over which we can lift the object easily. So we have to always keep between 45 to 90 degree, okay. The theta we always try to maintain between 45 to 90 degree, and if you want to have a better safe lift, then try to between 60 to 90 degree, okay. It is, you are seeing up how this after 45 degree the tension is abruptly increasing, and is 30 degree it is almost twice of the tension, okay. So you have to check this, the theta plays a very critical role. So in the case of bridal hitch you have to focus more on the theta, okay. Now we will move on. The second is basket hitch. Basket hitch is basically here the sling is basically wrap around the object, okay. Here the sling is basically wrap around the object. Packing is provided so that it does not damage, okay. It is basically basket hitch. Here their single sling is wrap around the single basket hitch. If double, there is a double wrap, then double basket hitch, okay. The capacity of basket hitch is affected by their sling angle. Here the angle also plays a very important role. Suppose we have to lift some shaft, so this is the shaft over there, so we have to place the sling in such a manner that it will not come out, okay. So the smaller diameter we have put up, or in basically these slings will be held by the friction only, okay, by the friction only. So if in order to prevent the slippage, these sling always be preferred to have an angle 60 degree or more, not less than 60 degree angle. You have to always keep these angles of the sling, these angles 60 degree or more, okay, not less than that, okay. Now we will identify how reduction factor, we will understand how reduction factor plays this role. The rope efficiency, basically when we are lifting something like this with the help of the eye of the wire rope, okay, then load is coming on the eye side, there is no issue. But in this case, in basically this basket hitch, in the case of basket hitch, the load also act on the body of the sling, so there will be bending over there. So there we have to calculate what is the rope efficiency in bending. So here here this D by D ratio plays a major role. D by D ratio is basically suppose this is the load that we have to lift it up, okay. It is having diameter D, and we have wrap around a wire rope small diameter D around this. So this basically the diameter of the curvature of the rope band. If the rope is passing like this, then diameter of this rope band is basically capital D, and small d is basically the diameter rope dia, okay. So there here this D by D ratio plays a very important role. Again, capital D is the diameter of the curvature of rope band, and small d is the diameter of the rope. So here the ratio is R is equal to capital D by small d. So we have the reduction efficiency reduction factor E. E is calculated, E is equal to 100 minus 50 divided by root R. First case when the radius is less than 6 inch, okay, and if radius is greater than or equal to 6 inch, then we have to use this formula. This is basically efficiency correction factor. E is equal to 100 minus 50 divided by R power 0.75. We will have an example for this. So you have to remember this formula. E is equal to 100 minus 50 divided by root R. E is equal to 100 minus 50 divided by R is equal to 0.75. Now this is correction. E is basically correction in efficiency, okay, efficiency correction factor E. So we have to calculate E first. If this E load reduction factor, if this E efficiency factor and the D by D, if we try to make it curve over there, then it is like this. This curve is like this. You are seeing up. This curve is like this. Okay. Efficiency, this reduction factor increasing as the D by D ratio increasing. Okay. So E is equal to less than 6 inches. E is equal to 100 minus 50 by R. E is equal to 100 minus 50 by r की power 0 point root r. This is root r and this r की power 0.75 is greater than or equal to 6. This is basically efficiency factor. Now the reduction factor, load reduction factor K2 due to bending. It is calculated using a formula K2 is equal to T2 into E by 100. 2 into E by 100. Okay, it is clear. Basically, whenever we are doing this, basket hitch, there are two things. First is the bending, and the second is the sling angle. Okay, so we have to calculate the reduction factor for both bending as well as sling angle. For the sling angle, the reduction factor is given by sin theta, but for the bending, the reduction factor, if we call it as sling angle K1, then it is called as K2, and K2 will be equal to 2 times E by 100, where E will be the efficiency, basically efficiency reduction factor E. Okay, so you have to remember this thing always. Okay, efficiency correction factor is E, so reduction factor due to bending K2 is equal to 2 into E by 100. With an example, it will be more clear. Okay, suppose we have to lift a shaft, and this shaft total weight is 28.8 metric ton, and we are lifting it using this basket hitch. We are using this okay, basket hitch. Now this is wrap around this is wrap around this. Okay, if the load is 28.8 metric ton, then the on each sling the load coming out to be 14.4 metric ton. 28.8 divided by 2, 14 to the 2 4 8, 14.4 metric ton will be the load coming on the each hitch. Okay, each basket hitch. Okay, now if capital D is equal to 14 inch, the shaft that we are lifting up, where the rope is the dia over where the rope is being wrapped around is 14 inch. Capital D is 14 inch. Okay, and we are lifting using a wire rope that is having small d is equal to 1 inch diameter. The ratio basically R is equal to capital D by small d. That is 14 divided by 1. That is basically 14. It is clear. We have to calculate the correction factor for both bending as well as the angle. Now SWL is equal to 8 into D square. We are using 1 inch dia rope, small d. So 8 into 1 into 1, 8 metric ton. It comes out to be this. Capacity will be 2 times SWL because we are using the basically two wrapping are there. Okay. Here is also T, here is also T. So the load is distributed by the W. It is like this. This it is like a pulley. Here tension T, here tension T, here W. Okay, so T 2T barabar W. So T is equal to W by 2. Okay, some that you will understand. That is whatever the capacity that is going to be double. Okay, the capacity will be 2 into SWL. It is the basic capacity. If we are not considering any correction factor, this SWL of the single wire rope is 8 into D square, but it is wrap around. It is like a pulley system having this like that, and weight is lifting that it will become 2 times. The capacity will be 2 into SWL. That will be equal to 16 metric ton. If we are not considering any correction factor, the weight is to be lifted is 14.4 metric ton, and we are getting 16 metric ton. Oh, then it is okay. But we have to consider the correction factor also, or the reduction factor also. First, reduction factor for the sling inclination. We are considering the reduction factor for the sling inclination. For the sling inclination, the reduction factor is sin theta. Here we are it is basically 90 degree. The angle is 90 degree. So we just put it angle sin 90 degrees equal to 1. So there the K1, the sling correction factor will be equal to 1. If it is some 45 degree, then 1.414, what will be the 0.414, that will be the correction factor. Okay, sin 40, sin 30, 1 by 2. It is like this. So the correction factor depends upon this. Now D by D is 14 by 1, 14, and R is equal to D by D ratio. R is equal to capital D by small d. That is basically 14. In the energy efficiency factor, we already discussed E is equal to 100 minus 50 by root r. R is क्या होता है capital D by small d, and E is equal to 100 minus 50 divided by r की power 0.75. Here the r is 14, basically greater than equal to 6. So we have to use this formula. Okay, so we are using this formula. E is equal to 100 minus 50 divided by r is equal to 0.75. So here it comes out to be 93%. For an approx we are taking up E 90%. Okay, this is the efficiency factor. Now we have to calculate the reduction factor, and reduction factor for the bending is basically calculated using K2 is equal to 2 into E by 100. 2 2 into 90 by 100 comes out to be 1.8. Now SWL will be SWL, oh, the required wire rope capacity will be SWL divided by K1 into K2. Okay, required wire rope capacity, what capacity we require, so we have to reduce, we have to find the wire rope capacity, then SWL that we try to lift, the weight we try to lift is 14.4 and the reduction factor is 1 is 1 and the other is 1.8, so it comes out to be 8 metric ton. So the SWL of the wire rope required is 8 metric ton and we are using 1 inch diameter, and it is also having the 1 inch diameter, having the 8 metric ton is already there. So 1 inch diameter wire rope is good for us, it is accurate basically. So this is the funda over there. We have basically, after calculating the reduction factor, just multiply by SWL. You just you can find the SWL. Otherwise you can SWL, the load you want to lift is given 14.4, just divide by the reduction factor, you will get the diameter of this wire. It is clear to you now. The other hitch is basically choker hitch, basket hitch. Now there is choker hitch. In the choker hitch, the same wire rope is passing through the eye, then it is like this. Okay, then it will be tied over there. Okay, if nothing friction will be experienced, then this it is like this triangle, and it will be having equal angle, 120 degree, 120 degree, 120 degree. Okay, this is called a choker's angle. This angle is called a choker's angle. Choker's angle. Okay, now if it is having the equal length, that is basically, if this is equal length and this angle is 120 degree, these two arms are same, so this angle will be same, theta. 2 theta plus 120 barabar 180, 2 theta barabar 60, so theta is equal to 30 degree. In this manner, this angle comes out to be 30 degree. Okay, this is the feed body diagram. Here basically there is some slippage over there due to friction. It is, so we have to, in practice it is not like this, there is some changes over there. Okay, so this, there is a choker angle. Apart from the angle, you have to use the choker angle reduction factor, that is choker hitch angle. If it is between 105 to 120 degree, then reduction factor is 0.82. It is between 19 to 105, reduction factor is 0.71. 60 to 90, reduction factor is 0.58. 0 to 60 0.50. This is the choker angle. Is what angle? This angle is basically choker angle. So based upon the angle, you have to just multiply it SWL with this angle thing. Okay, then you will get your answer. Okay, so this is the final. So we have covered all hitch over there. Okay, the major is D by D ratio is very important, and this bridle hitch is very important. Or if you want to know the basically the mechanics behind it, I already covered in the previous lecture. You can go through that also. Okay, hope you like this video.